Okay, good morning, class. So before we get into what we're going to talk about today, I just want to make sure you guys really understand what we talked about last week, which was nebular theory, if you recall. Because what we're going to be talking about today is planetary formation, and understanding the nebular theory is extremely important for understanding planetary formation. So before we start, is there anyone that can explain nebular theory to me? Okay, yeah, that's perfect. Yeah, so you have this huge cloud of gas and dust, and something happens. There's like a force or a supernova or something that will begin this process of clumping the gas and dust together. We're not entirely sure what it is, but we believe that it's mostly supernovas. Um, so yeah, the gas and dust kind of collects together, and eventually, if there's a sufficient clump, gravity will take over, and everything will start to collapse. And once you get to a certain point, a certain pressure, then there will be enough internal heat energy to where nuclear fusion will actually start, and that's how you get a star like our sun. So now that we have a sufficient grasp of what the nebular theory is from what we learned last week, one of the key things that you're going to need to know today is that a larger mass means having a larger gravitational force. That's going to be a really key sentence for you to know. So before we go any further, I want you to write down in your notes in big bold letters as big as you can, however it takes for you to remember it, that a larger mass means a larger gravitational force. Okay, so now we're going to get into the good stuff. A lot of what we're going to be talking about today has to do with gravity. So make sure you really understand that. And if you don't feel like you have a really good grasp on it, maybe you should come and see me after class or, like tomorrow morning, just whenever you can, because it's really, really important that you understand gravity. Um, okay, so the good stuff. So what we're going to talk about first is a really vital part of planetary formation, and it's called the accretion theory. Okay, so what you need to know about accretion theory is, if you remember the protoplanetary disk that we talked about from the nebular theory, there's all of this extra gas and dust revolving around the protosun, right? So what happens to all of that gas and dust? Can anyone give me a thought or a theory? Yep, that's exactly right. So that gas and dust is how we get the planets in our solar system. Um, so the accretion theory is kind of similar to how the sun was formed, where there's this clump of material, this clump of gas and dust that happens to be a little bit more compact than the other things around it. So it starts to collapse. And that collapse creates what we call a protoplanet. It's this little clump of rock and gas and dust that will eventually become the planets we know today. But before it can do that, it has to collect some more material first. And that's what the accretion theory is. So, what we talked about earlier, the sentence that I had you write down, that something that has most mass will have the greatest gravitational force, right? So these protoplanets that are revolving around the protosun, as they're kind of making their path through this disk, because they have a stronger gravitational force, because they have more mass, they're picking up all of this extra material that they happen to come across in their path. So a good analog for this that I discovered is have any of you ever made snickerdoodle cookies, where you take the dough and you roll it in cinnamon and sugar? Well, at least that's how I make them. I don't know how you make them, but you take this ball of dough and you roll it through cinnamon and sugar, and it kind of picks up the stuff that it comes in contact with. And it's a really similar theory to the accretion theory with the planets. Okay, so that leads me to my this next part of the lesson. Are planets all the same size? No, of course they're not. So which planets are the biggest? Can you name them? Yeah, that's right. Jupiter, Saturn, Uranus, and Neptune. And the smallest? Mercury, Mars, Venus, and Earth. That's right. So why are the planets different sizes? Do any of you have an idea? Yeah, so that's right. So the Jovian planets are mostly gas. I'm sure most of you have heard of that. So why is it that they're actually the biggest, though? Like, why do they have gas when the terrestrial planets don't? Okay, so in order to answer the question why the Jovian planets have more gas than the terrestrial planets do, we actually have to define a new theory. It's called the frost line theory. So what I'm going to have you do is get in your groups, just at your tables, and I'm going to give you some Legos. Yeah, I know, Legos, right? So what you're going to do is you're going to build the largest structure that you can out of the Legos that I give you, okay? And then I'm just going to give you a few minutes, and afterwards we're going to compare everyone's structures. So have at it. You can get the Legos from your workstation. Okay, so now that you've had a few minutes to build your Lego structures, so I want you to just look around the room. Um, who has the biggest structures here? Yeah, groups two and group four, right? So how come their structures are so much bigger than the rest of yours? Yeah, because they have a lot more Legos, right? They have those blue Legos. So this is a really good analog for kind of what happened with our solar system, actually. So for the groups that only had yellow and red Legos, how many Legos did you have? Not very many, right? So you really could only build small structures. But for those of you that had the blue Legos, you had at least 3 times more Legos to work with, right? This is what happened in the solar system, actually. So the Jovian planets, the big gas giants, they actually formed in a situation where they actually had more material. They had ice, actually, and ice made up a lot of their mass. Unfortunately, the terrestrial planets were in a position where they couldn't use ice to form their masses because it was too hot, and that's where the frost line theory comes in. So the frost line theory is this kind of magical idea where there's a certain distance from the sun where the temperature in the solar system is cold enough for gases to turn into ice. Particularly, it's the like water vapor, water gases, and also methane gas. Um, there was a point, and it's actually between Mars and Jupiter, where the temperature was cold enough for ices to form. So, as the protoplanets were rolling around in this protoplanetary disk and collecting gas and dust, um, it just so happens that the location where the proto Jupiter and the proto Saturn and all of the proto gas giants were, there just happened to be a whole bunch more material, particularly solid ice. So, because of that, they had a higher mass, and as we discussed earlier, the more mass you have, the higher gravitational force that you have, right? So because they had these much greater masses, they had a much greater gravitational force as well, and that's where the gas comes into play. So gas, because it moves so quickly and it's so light, it's only the most massive planets that have the highest gravitational force that can actually hold on to those gases. So why doesn't Earth have hydrogen and helium gas? That's right. So because the Earth formed before the frost line in distance, the Earth didn't form with ice, which means that there was a lot less mass for the Earth to use. So, because it's less massive, it wasn't able to hold on to those lighter gases like hydrogen and helium. The gases were moving too fast, they were too hot, and the Earth just wasn't strong enough to hold on to them. Okay, so with the time remaining, what I want you to do is I want you to fill out this handout that I'm going to pass around. So it's a graphic organizer. So there's some pictures that you need to label as well as some questions that you need to answer. So get in your groups and you can work together as a group as much as you want, and yeah, just get on that. If you have questions, I'll be walking around the classroom.